The next two videos are going to discuss estimating parameters. And when you think about parameters, these are measures of populations. So we're going to start leaning further into statistical inference when we're making inferences, generalizations about populations from a particular sample. And the ability to do so is going to be based on our sampling distribution, as we talked about in the previous video. In part because our sample is going to affect our estimates of the population, and partly because of the error in these estimates. Based on our sample sizes, we will have certain levels of confidence in our ability to estimate the parameters of the population of interest. And this goes back to the central limit theorem that we discussed in the previous video, which in part is determined by the standard error of our particular sample. So when we're thinking about inferential statistics, we have two major areas of interest, and the one that we're going to focus on for the next two videos is, again, estimating population parameters. And part of this is understanding how close our particular estimate is to the true population value. The text goes into this in section 6.1. So we can think about our standard normal distribution, and we should be comfortable now using the Z formula to standardize our respective information to this standard normal distribution and to be able to understand the area under the curve and the probability of a particular event occurring. But as we discussed in the previous lecture, this relies on our understanding of the population mean and the population standard deviation. And at times we're not familiar with what the population standard deviation is. Now we might think that we can just replace this with the sample standard deviation, but we run into some problems with this because this then leads our sample to start deviating from normality, which then becomes problematic when we're conducting statistical tests. And one thing that we know is that sample size plays a role in our ability to estimate parameters and also the shape of our distribution. And as our sample size decreases, we tend to see less of a normal distribution in our respective data. So how do we go about alleviating this potential problem? Well, we can use other sampling distributions to understand our data and to quantify the probability of a particular event occurring when we don't know the population standard deviation. So the first of which that we're going to discuss is the t-distribution. So this is really similar to the standard normal distribution, but it's for sampling distributions rather than other probability distributions. And it's similar in that the distribution is going to be defined by the mean and the standard deviation. However, these are going to be for the sample, but it's also defined by this new term that we have, degrees of freedom. And the degrees of freedom takes into account sample size, and it's in this particular distribution defined by n minus 1, so the sample size minus 1. And what this does is it accounts for the departure from normality when we make substitutions between parameters and statistics. And so it's useful to think about the t-distribution as having the same general properties as the z-distribution, except for a couple key factors in that we're using the sample standard deviation instead of the population standard deviation, and we're taking into consideration sample size, which we know from the central limit theorem plays an important role in the shape of our distribution and our ability to estimate the parameters that we're interested in. And this is inherently built into the formula in which we convert our data into this t-distribution. So in thinking about the value of these distributions, one way to utilize these different distributions is to assess if we have any kind of statistically significant patterns that are occurring in the data that we've collected. And for the standard normal distribution, for the z values, we've got specific thresholds that once they're crossed, we know that there's some kind of a significant effect occurring in the data that is being observed. And those thresholds are negative 1.96 and 1.96. For the t-distribution, there's no standard threshold. The threshold is going to change based on our sampling distribution, which is going to be influenced by our sample size. We're going to talk about this. So if we think about our z-distribution, we have our associated z-table, which then provides us with the area under the curve and the probability that a particular event is going to occur. So on the first row in the first column, we have our z-scores, and then within the center of the table, we've got our probability values. And this then helps us determine the likelihood of an event occurring that we're interested in. And as z increases, our probability value also increases. So we have this direct relationship here. Now, for the t-distribution, we also have a table, but this table is new, and it's also slightly different. However, we're going to walk through this, and we'll talk about it in class. So the first major difference is that the center of the table represent the t-values, not the probability distributions, or not the probabilities. So the first column represents the degrees of freedom. Again, this is going to dictate our distribution and our ability to determine if we see some type of significant effect or not. And this top row is our probability. So we've made some slight changes here, but as we'll work through problems in class and in practice in these video lectures, you'll become more comfortable using this table as you are using the z-table. One thing that we notice is that as our probability value decreases as we move from left to right, our t-value increases. This is an important trend that we notice. And also as our degrees of freedom increase, our t-value decreases. So what does this mean? So the t-values are similar to the z-values in that they provide us with a threshold in which we need to overcome, in which to determine if there's some type of statistically significant effect in what we're observing or not. And these t-values are affected by the degrees of freedom, which are influenced by our sample size, as well as the probability that we're interested in setting as our threshold. We'll talk more about this as we move forward using this t formula and doing t-tests in future lectures. So we can use this t-distribution to estimate population parameters when we don't know the population variance. If we're aware of the population variance, we'll use the z-test or the z-distribution. One important caveat, though, is that for the student's t-test, t-distribution, we shouldn't be using it when our sample size is relatively small and our population isn't normal. Now, we might not know if the population is normal or not, but again, going back to the central limit theorem, we can assume that our sample is going to be normally distributed if our sample size is greater than 30. For this particular course, you'll be provided with data and you will be indicated when to use this particular distribution or not. But in general, when we're thinking about this t-distribution, it's going to serve as a replacement for the standard normal distribution when we have less information about the population. And the reason that we want to avoid using the t-distribution when our sample size is small is that as our sample size decreases, we tend to see more variability in the data, which is what we would expect based on the central limit theorem. And so with smaller sample sizes, we tend to see deviations from normality, and in turn, this leads us to potentially make inferences which are inappropriate. And so this figure here shows that as we move from the yellow to green to blue to red curves, decreasing our degrees of freedom, which is based on our sample size, it tends to flatten the curve and spread it out a bit more. And so our variance is going to increase, and so our confidence in our estimates are going to decrease. When the degrees of freedom become very large, we actually see that the t-distribution approaches the same shape as the standard normal distribution. and this is useful for statistical tests, so we should be aiming as scientists to have appropriately large sample sizes to describe our populations. And for more information on this, check out section 9.2 of the text. So, in getting to the theme of this lecture, this parameter estimation is using sample data to estimate our population parameters, and we can use the distributions like the t-distribution to do so. Now, for parameter estimation, there are two key components that we're going to discuss in detail in the next lecture. The first of which is point estimation, and so this is just a single value that is our estimate for the population parameter, so maybe our sample mean, estimating the population mean, and also interval estimation. And so in addition to providing a point estimate, a single value, it's also important to provide a range of values over which we feel confident that even if our population parameter is not exactly the same value as our statistical point estimate, that it falls within that range of values, and we can indicate how much confidence we have in this particular range of values. So when we're thinking about these point estimates, we're not really sure how close it might be to the actual mean of the population. We just use statistical theory to suggest this is a good indicator of our population mean, and this is then supported by our interval estimate, which provides us with the margin of error to say how accurate and precise we are with our particular estimate. If we have a very wide width of confidence, then it would suggest that we don't have a lot of support for our point estimate. But if our interval is very small, then the support for our point estimate is quite large. And so we need to have both point estimates and interval estimates when we're estimating the parameters that we're interested in, for instance, population mean. Couple important things about this parameter estimation is that it should be unbiased, as we've been talking about throughout the course, and so random sampling is important, and this is going to help ensure that we're not specifically choosing certain individuals or observations for our particular sample. And it's also good to aim to reduce the amount of variation in our particular data, and we know based on the central limit theorem this is directly related to our sample size. As our sample size increases, we tend to have a decrease in variation, and this again will lead us to have a stronger level of confidence for estimating those parameters from our point value statistics. So in the next lecture, we'll talk about estimating these parameters when we know population variance and when we don't know population variance.